Now we want to turn to just a little bit more of a general problem, which is sometimes you want to be able to write the integral of one power, or the integral of an arbitrary power, the nth power of a trig function in terms of a lower power. This is similar to the example we just did with secant cubed, but we want to make it a little bit more general. There's actually a name for this, which is called a reduction formula. And it sort of makes sense because imagine that I could keep reapplying this formula repeatedly. I could basically find the antiderivative of any power of cosine because if I keep subtracting powers two at a time, then if I start with an even function of cosine, I'm going to get down to cosine x, whose antiderivative I know. If I start with if I start with an odd power of sine, I'm going to get down to the first power of cosine. If I start with an even power of cosine, I'll eventually get down to cosine to the 0x dx, which is just, since cosine to the 0 is just 1, that's just that expression, and I know how to evaluate that. So that's why it's useful to do this, because eventually I can always get far enough down to an antiderivative that I know. So I just want to show you how to derive something like this. So we're going to do this actually, once again, by integration by parts. And the trick to doing it is we're going to write u equals cosine to the n minus 1x, and dv is equal to cosine x dx. So let's just pause for a minute to agree what u and dv is equal to. So now we're going to write du. It's a little complicated, but I'm using the chain rule here and the power rule together. So it's going to be n minus 1 cosine n minus 2. Sorry, forgot actually one of these. N minus 1 cosine n minus 2, and now the inner function itself is cosine, so I need a negative sine x dx like that, and here I have v is just equal to sine x. So that allows me to write that the integral of cosine to the nx dx is equal to uv, so cosine to the n minus 1x sine x. Now let's look at what I have here. I've got to multiply v and du. First thing to note is that I have a negative sign here, so when I subtract v du, it's going to really be like I can just take that negative sign out and add. So let's see what I have here. I've got n minus 1. Keep in mind, n is not a variable. N is a constant, and that's why I don't have to treat it especially under the derivative rules. I can treat this just like it was the number 105 or something like that, because it is, because n is fixed. It's not a variable. So n equals, so what I have now is cosine to the n minus 2 of x, and I have two factors of sine, so this is going to be sine squared x dx. Now isn't this nice, because as we know, sine squared, cosine squared, these are sort of magic terms in calculus because we're going to be able to run them through the identities that we know. So let me do a little bit of simplification here. I'm going to take out this factor of n minus 1. I can do that. Once again, I know that many of you say, well, wait, how come this doesn't work? The reason this doesn't work is because x is a variable, but if I have, say, nx to the 100 dx, there's nothing wrong with rewriting that as nx to the 100, like that. I can always pull out something that's not the variable in the problem. Just because it's written symbolically, it's still just a number. So this is going to be the integral of cosine n minus 2x, and sine squared, I'm going to rewrite it as 1 minus cosine squared. So we keep going. This becomes cosine n minus 1x sine x plus, this is going to be n minus 1 integral of cosine n minus 2x dx. And now I've got this n minus 1, and I'm multiplying it by that term there, that minus. So it's going to be minus n minus 1 integral of, I have cosine n minus 2 times cosine squared. So if I take, I mean, think about this. If I have x to the 98 and multiply it by x squared, I just get x to the 100. So I'm just adding 2 to the exponent, and conveniently n minus 2 plus 2 just comes out to n. So this is going to be cosine of nx dx. Now, conveniently, look what I have here. I have cosine nx dx on the left side, and I have n minus 1 copies of the same integral on the right. So what I'm going to do is I'm going to add this. I'm going to add n minus 1 of that integral to both sides of the equation. That'll cause it to disappear on the right, and on the left I'm going to get n minus 1 plus 1, because this was, of course, just equal to 1 cosine to the nx. So this is going to be cosine nx dx equals cosine n minus 1x sine x plus n minus 1 integral of cosine n minus 2x dx. There we go. And on the left here, I'm just going to combine these terms so that now what I have is n cosine to the nx dx. And now you can easily see how we finish the problem. I just divide everything by n. That gives us cosine to the nx dx is equal to 1 over n cosine n minus 1x sine x plus n minus 1 over n cosine n minus 2x dx. So this is how we would rewrite the formula. We would rewrite the integral of cosine to the nx in terms of the integral of cosine of 2 powers lower of cosine, and this is once again what is called a reduction formula.